It's actually first year graduate student. You could make this plot. Okay? And it's not that hard. So the only tricky part is that did you use the right data, blah, blah, blah. How much data did you use? And knowing how to do that takes, relying on other people. So you have to share information with folks.
And actually something that happens sometimes is somebody will make the same version of the same plot as you made with their analysis software, and they'll get something that looks different.
It's like a problem set.
And then you have to scratch heads and see who's doing something wrong.
It's like working on the problem set together, and you realize I didn't get that for part 4. What's going on? And you go back and you check. And so the advantage to having like 20 different people working on exactly the same thing, is that you're pretty sure it's correct when you're done. Unless you all made the same mistake, which that is a concern. But then there's another experiment across the other side of the accelerator that does the same kind of physics, Atlas. And so they will also independently verify with separate apparatus. So if our calibration's messed up, they have a different kind of different kind of calorimeter, and they will have different kinds of calibrations. So that's part of why they're doing.
And you can imagine when we presented our new result on Tuesday that the other experiment immediately started multiple analysis groups looking for the same thing. And they won't be shy about telling us if they don't see it.
So part of this is you see something you don't expect. You're putting your money on the lines to say, we think this is right, and we're going. And it's actually, that paper was just accepted today. Shockingly, it was submitted like Tuesday, already accepted by the journal. Amazing, but clearly of great interest. So people read it, and the editors said, good, we like it.
It only went out, the collaboration only agreed to submit it on Friday.
Last week, and it's already published. It's online publishing. So anyway, the environment is a little bit different than like, I'm going to sit in my office with my pencil and paper and write my paper, or my computer. You're writing parts of it, and other people are writing parts of it, and you kind of bring it together.
So how long did it take to get everyone to approve the final draft? Between the measurements.
That particular thing first appeared in July. And then they actually threw multiple teams at it to cross-check.
They did a lot of cross-checks.
And I think it was early to mid-August when they started seriously, okay, we're time to think about going public with the paper with this. And since then, there's been a series of internal reviews and presentations. So there's a whole sequence where people get up, put forward that this is something that should go out to the world. Other people say, no, but you need to do that check. And the balancing act is that you don't get bogged down. If 1,000 people all suggest different checks to do, then you will never publish anything. So there's a committee called an ARC that's sitting there judging.
The Analysis Review Committee. Yeah.
Sitting there saying, you know what, that's actually a really good suggestion. You better check that out. They'll say, well, that one, he doesn't know what he's talking about, just ignore it.
Or you already checked that, right? Remember you did this thing, which if their hypothesis, what's wrong, is true, then it would have already shown up in this plot. So, and I don't know in this case how many pages the plots they had, but my guess, we saw talks that were given.
Well, I looked at some of the early
notes. 60, 70 pages worth of stuff presented publicly to the whole world, actually, at CERN. And that's just what was shown publicly. So you can imagine.
For every one of those pages, there's pages and pages of work that's gone into it.
And I don't know how big that team was, but it was predominantly probably the work, again, of 10, 20 people. And then when something interesting was found, they probably went and got 5 or 6 other guys and said, look, you got to check their work because this is bizarre.
Yeah, so they put 2 other teams on it to work independently and run different analysis code so that you can rule out that it's just a coding error.
So one thing they did is they were looking at charged particles coming out to see that ridge. They also did a check where they looked at photons or neutral energy in the calorimeter, and they also saw consistent but not as much statistical power in the peaks, but they saw the same consistent thing. So they couldn't say, oh, it's just you don't know how to find a charged particle in your detector. Because also the photons were showing this too. But the photons were mostly coming from neutral pions. The charged particles are mostly charged pions. So they actually are showing you the same physics, what you expect if it's due to quark-gluon plasma type thing.
So other questions?
I have a question. This is more about the technology technology and engineering, I guess this, things I don't know much about the field. Does the LHC sort of make any of the old colliders obsolete and sort of, or is there still new science that can be done at the lower energies that is still interesting?
Yeah, so at the moment, the Tevatron and Fermilab has higher luminosity but lower energy. And there's a trade-off between the two. So there's some things that we can do that they can't do because of energy. But some things, like looking for the Higgs boson, they're actually competitive with us for now. At some point, the luminosity will surpass them. Then we'll have higher luminosity, higher energy, and the physics program at the Tevatron will change. And they'll just go after completely different complementary stuff and not chase after the Higgs boson anymore.
Another way to answer that, which he's hinting at in his answer, is they'll go after other physics. So what you can do is you can look for the new particles to be produced directly. Or the other approach is to say, let me collect a lot of data and look for very rare things that could happen. So for example, if there's supersymmetry, you can make a process where the supersymmetric particles are interacting with particles you know and love and change the answer that you expect to get from some, for example, in CP violation, which now we're getting pretty technical, but you would expect something from the standard model and it could be enhanced or diminished or canceled exactly by supersymmetry. And so people like Marge Cochran, who's another professor here, are interested in looking at some what we call really rare processes. And the Tevatron is already planning to use their proton beams, which are very intense, to make them even more intense, to use them to make lots of low energy particles that can be used to probe these rare processes. So they're looking for a muon to convert into an electron and a photon, which is something that conserves charge, but it changes a muon into an electron, and that's not something the standard model lets you do very easily. It's predicted to be very, very rare in the standard model, but it could be enhanced by factors of billions or more by other particles that we don't know. So you could test things at the low energies as well. So they will do that. They'll do neutrino physics as well with the proton beams. So those things are not directly going for the high energy particles, but will be complementary.
Non-physics question. So this science seems to have produced like more nonsensical stories in media than most other fields of science about many black holes and people coming back from the future and presenting the discovery of the Higgs and things like that.
You don't believe we're not from the future?
I'm not. I personally don't think that's necessary.
He's getting younger every day.
Exactly, because it gets people talking about it. I was wondering what your opinion is as a scientist actually working with it.
So one of the effects it's had, and there's huge interest, is that there are actually very strict rules in the collaboration about not shooting around launch. So we were strictly forbidden to say anything about, say, this effect that's been seen until it was approved to go public. And that's to try and cut down all the speculation and chatter. There's been some cases in the past where it's gone around the blogosphere that the Higgs has been discovered at Fermilab and things. And we're trying to quench that. But one of the interesting things with the web is there's no editorial process. Anybody can put anything out there. And some things, you will often have, so we all know from quantum mechanics that there's some probability that I'm just going to vanish from here and appear on the other side of the Earth by tunneling, right? And you can calculate the probability for that. And it isn't going to happen in the lifetime of the universe, but there is a finite probability for that to happen. There is a school of theorists who calculate the moral equivalent of that for LHC things, but don't then apply the filter and say, but you're never going to see it happen. And then the press hears about this possibility and they get very excited, gets misunderstood. And it's so, when it comes from physicists, it's the moral equivalent of saying we're going to appear instantaneously on the other side of the Earth.
And do you think there's a positive side to that because it gets people talking about it?
Yeah,
LHC?
there really isn't bad press, right? I mean, that's a maximum. That's not completely true, right? You could do something horrible, but
I think blowing up the accelerator, which we did a few years, wasn't exactly the press we wanted.
yeah, we didn't want that. We got lots of press. So.
And they never used the word explosion, but I don't know about you, but rapidly progressing shock waves, displacing magnets. They used every word you can imagine without using the word explosion. They blew it up.
They keep on talking about incident. It was more than an incident, the disaster. They fixed it, and it's working great now. That's actually good. And that made the news, too, so we can be happy that there was good news, too. One other thing to think about, maybe explaining why people get so worked up about it, it is a really giant thing. And when the Brookhaven lab turned on their collider, that was accelerating beams of gold atoms and things like that, and crashing them together, there was a similar, you might make a new state of matter that will be more stable than normal nuclear matter, and it will suck, they'll turn the whole detector into a giant blob of strange matter, and then it will eat up Long Island, and eat up New York State. The whole, Earth will collapse into a black hole or into a strange star. Okay, so that happened before, too. And I think it's just the scale of it. This is the biggest scientific experiment ever undertaken. And that drives people's imaginations to positive and ridiculous at the same time.
So apparently we're destroying the planet on November 9th. So factor that into your plan.
And I get some more strange ones, so watch out.
I thought you were doing that in 2012.
Yeah, all right.
Well,
Are you going to blow up the Vatican too, or is that?
Maybe. No, I doubt it.
Trying to count the red.
The only thing accurate about that movie was the Swiss accents of the Swiss guards in that. Almost the only thing accurate.
so if you search LHC on Google, you get this world ends at CERN, November 9th.
Somebody's paying for that.
Somebody's paying money.
It just goes to show Google doesn't apply a filter. As long as it involves cash.
Yeah, so you go to these guys, and it's...
It's a wiki.
No, this is somebody, CERN3. It catalogs all the ways we're going to destroy the planet. And the next moment of opportunity is November 9th. That's when they start the gold-gold collision. So the idea here is the gold-gold collision is going to produce strangelets that will consume the Earth.
So one thing that connects all of this back to this discovery is, if indeed we could make some new form of matter at the LHC, it wouldn't be the first time such a thing could happen, because cosmic rays are raining on the Earth all the time from astrophysical sources. And they have energies that actually are even higher than we can make in the LHC. And the difference is the LHC has been on for, eternal total time has actually been running is way less than a year. And cosmic rays have been hitting the Earth's atmosphere forever, basically. And none of them resulted in a black hole that devoured the Earth or strange matter that made us into a dark star or something. So that's actually a more scientific argument that says the plausibility is even reduced more than just taking the calculation and saying, it's 6 million times the age of the universe is how long we have to wait before somebody tunnels to the other side. I don't even know. That's probably an underestimate of the Earth. But so that, we know that protons or whatever else is coming in cosmic rays, nuclei even hitting the atmosphere, don't do much of anything interesting at all. Well, lots of interesting stuff. But we'd love to get it to happen inside our detector where we can study it. So no strange matter probably, but at least no strange matter that's going to gobble up the universe.
Well, gentlemen, it's almost 1 p.m. We need to wrap up. So let's thank our panelists. Until next year. Appreciate you coming.
Yeah, thanks for inviting us.
Take a sandwich.
Yes.